Alright, so hi guys. So in the previous video we talked about first order reaction. We also talked about the unit for the rate constant for a first order reaction. We ended it with talking about the half-life of first order reaction, and we did a simple calculation on that. So in this video we're also going to talk about the second order kinetics. We're going to derive this second order rate equation. We're also going to talk about the rate constant for a second order reaction. And finally, we're going to talk about the half-life for a second order reaction. So, so for a general reaction involving a single reactant as the reaction above, the rate form can be written as, so rate form is the same as negative 1 over 1 change in concentration of B over the T equals to K B square. So because the coefficient of B here is 1, we have this 1 over 1. So, and because this reaction is second order reaction, so we have that the concentration of the reactant is raised to the power of 2. So for us to derive the second order kinetics, so the first thing we need to do is to put this negative sign to the other side, so we can have change in concentration of B over the T to be equals to negative K scale of the concentration of B. So the next thing we need to do is to multiply through both sides by the T and divide both sides by the scale of the concentration of B. So we have that the B over the T multiply the T over the concentration of B scale. So we have this to be negative K B scale. So we also multiply the T over B scale. So the T cancels the T and this also cancels the. So we are left with change in concentration of B over the concentration of B scale equals to negative K dt. So let's take the integral of both sides. We're going to have, so we're going to have x equals to 0, x equals to x, and we're also going to have change in concentration of B over B square equals to t equals to 0 or simply 0 and here t. So we have minus k dt. So when we integrate, we're going to have we're going to be left with this one becomes, so we have this to be b minus 2 plus 1 over minus 2 plus 1. So we have this and we have x, we have new here. So equals to minus kt. So we have x and 0 here. So let's evaluate this. So we're going to be left with b minus 1 over minus 1 equals to negative kt. We have x and we have 0. So therefore, this becomes negative 1 over b equals to negative kt. Remember that we still have our x and not there, and here also x and not here. So let's put in these values here when x is x and when x is initial, which is 0 here. So we have that 1 over b x minus 1 over b naught equals to minus kt minus k times 0. So therefore we have that minus 1 over b x plus 1 over b naught equals to negative kt plus 0. So we are left with this, and we can therefore say that negative 1 over bx equals to negative kt minus 1 over b naught. So when we multiply all through, we have that 1 over bx equals to kt plus 1 over b naught. So we have this. So this is the final concentration. This is the initial concentration. So we can also write it as this below. So we can have it as 1 over b minus x. So we have kt plus 1 over b. So it's still the same thing. So looking at this, we can represent it using the straight line equation of mx plus c. So this is the y-axis, this is the x-axis, this is the intercept, or sorry, this is the slope or the gradient, and this is the intercept. So y equals to 1 over b minus x. So our our k which is also the m, equals to the k. So our x, so the x here equals to the time. So our intercept c equals to 1 over b. So we have a graph. So the y-axis is 1 over b minus x. So the x-axis is time in any unit of time. So this is the slope, and this is the intercept. This is the intercept on on the graph. So let's talk about the half-life of a second order reaction. Okay, before we talk about the half-life of a second order reaction, let's quickly get the unit. Let's solve for the unit of rate constant for a second order reaction. So the units of K for second order reaction. So we have that since the final equation is this, we don't have to use this. Remember that the rate form is K into bracket concentration of B raised to power scale here. So the unit of rate is always molar per seconds. So we are looking for K, but we know that our concentration is in mole per dm cube, or molar, like this. So we have scale here. So the unit of K becomes mx minus 1 over m square. So this cancels this to give m, and this becomes this. So we are left with m minus 1 x minus 1. So this m can also be mole per dm cube. So we can therefore express this to be this. So we have it to be mole dm cube minus 1 s minus 1. So we can therefore say that mole minus 1 dm cube s minus 1. So this is the unit for the rate constant for a second order reaction. All right, so let's talk about the half-life for a second order reaction. So recall that the second order kinetics has the equation to be b minus x equals to kt plus 1 over b. So let's put it in brackets here. So at half-life, our final concentration becomes initial concentration over 2. So at half-life is the time it takes for the initial concentration of the reactant in a reaction to decrease to half of its initial value. So we can therefore say that 1 over b all over 2 equals to kt half-life plus 1 over b. So therefore this becomes 2 over concentration of B equals to K half-life plus 1 over B. So let's collect like times. We have that 2 over B minus 1 over B equals to K T 1 over 2. So therefore we have that this becomes 2 minus 1 equals to KT 1 over 2. So therefore we have that 1 over B equals to kt 1 over 2. So therefore, we can say that the half-life for a second order reaction becomes 1 over B, and let's put the K here. All right, so it's important to recognize the difference between the half-life for a first order reaction and half-life for a second order reaction. So let's quickly talk about the little difference between the half-life of a first order reaction and half-life of a second order reaction. So for a second order reaction, the half-life depends on both the rate constant and the initial concentration of the reactant. So the half-life of a second order reaction is inverse of the rate constant and the concentration of the reactant, the initial concentration. So, but for a first order reaction, the half life depends only on the rate constant. So, looking at the equation here. So, also for a first order reaction, a constant time is required to reduce the concentration by half and then by half again, and so on as the reaction proceeds. So, this is not true for a second order reaction. What I just said is this: for a first order reaction, like a constant time is required to reduce the concentration of the reactant by half. So let's say the initial concentration of the reactant is B. So the time it takes for this concentration to decrease by half and then by half again is always a constant time. All right, so let's look at the question here above. So a reaction obeyed the rate equation, changing the concentration of x over the t to give rate constant times the concentration of e raised to the power of the fraction 1 over 2. So where x is the product, so what will the unit of the rate of the specific rate constant be if the concentration is in molar and the time is in second? So for us to do this equation, for us to do this, to solve this question is very simple. What you need to do is that since this one is changing concentration over changing time, I recall that we said that concentration is in molar, and also do always remember that the rate of a reaction is always molar per second. That is concentration over time. So we have that the rate equals k a 1 over 2. So therefore we have that molar over second, which is time, equals to k, and then we have molar 1 over 2. So therefore we can say that this raised to power minus 1 equals to k raised to power 1 over 2. So therefore we can see that k equals to x minus 1 over m1 over 2. We can therefore express this as 1. This is the same thing as raised to power 1. So minus 1 over 2 s minus 1. So let's say this 1 over 1. So we have that this to be over 2, and then we have this to be 2 minus 1 s minus 1. So we have that m equals to 1 over 2 s minus 1. So you can even go further to express the above answer as since molar is the same thing as mole the m cube. So we can say that we have this to be mole 1 over 2 dm cube minus 3 over 2 s minus 1. So it's still the same thing as this. So that is the answer.